Welcome to Rubber Duck Engineering. This week, we're going to continue exploring machine learning and tic-tac-toe. We're going to do it the AlphaZero way.
AlphaZero.
AlphaZero. Hey, Eric, how are you? Welcome back.
I'm back. It's great to be back. Sorry I missed last week's show. I was in a hotel with flaky Wi-Fi at a 6 a.m. flight, and it just wasn't going to happen.
You know, it's much harder to do the show without you. I really appreciate the partnership here.
I was trying to write some code this afternoon. I didn't have anyone to talk to, and I remembered how dependent I am on Rubber Duck debugging.
Did you pull out like an actual rubber duck and start talking to the rubber duck?
I didn't, and I should have.
Don't you have the Captain Picard rubber duck from the?
They're in the other room, but yes, I do have a Captain Picard rubber duck. Which my hair grew pointy several years ago, and I'm a manager and all that, so I don't write a lot of code. But I was trying to write a little bit of code this afternoon, I realized how dependent I am on being able to think out loud with someone. So tonight we're gonna do AlphaGo. I still have not actually watched last week's. I know you gave me a little side tour. You used a different bridge?
Yeah, so last week we were doing tic-tac-toe, but we were doing reinforcement learning.
Mm-hmm.
And it turns out it's not a great fit for these kinds of games because reinforcement learning is sort of expecting you to get a little bit of reward all the time. And that's sort of what feeds back into training the model. Whereas in a game like tic-tac-toe, you play for a while, you don't know what's going to happen, and then either you win or you lose. And so it turns out the same people, I think it's DeepMind, AlphaToe, yes, exactly. The same research group
totally should have named it that.
The same research group that did the Atari thing that we talked about last time. I don't know what their next paper, but some later paper they did was on a different technique that was more for board games. So they did Go, then they did chess or whatever, and then I found this great tutorial, which is what the banner that Eric just put up, that was sort of explaining, breaking down the concepts in that paper to be more accessible to people like me. And then also this person has a GitHub repository where they've actually implemented these techniques in like 3 different machine learning frameworks, including PyTorch and TensorFlow. And they've applied it to a whole raft of games, including tic-tac-toe. I didn't look in the tic-tac-toe folder. I did look in the Othello folder to like learn what it was, but I thought looking in the tic-tac-toe folder was a little bit too close to home. I wanted to do a little bit of the discovery myself.
I was talking with one of my mentees this afternoon, and I didn't mention this, but it was in my thought process, and talking about sort of like when you learn art, the importance of like copying masters.
We're definitely in the like master copy phase.
Correct, we're in the master copying phase. So I actually don't think it would have been terrible if you had read the.
Well, I didn't want to just like copy it, just copy and paste it all and then run it and be like, oh, it did the thing, right? I wanted to like go through it line by line, like understand what does this line do? What happens if I don't do this? That's sort of my learning process for exploring a new area like this.
Mm-hmm. We have to break it. We talked about this probably a couple of weeks ago when we did the before Flutter thing. I remember learning so much about the web and about Blink and all the things that we had fought for years as we tore it apart.
This happens in like the medical community too. Like you don't learn a lot in medicine by studying healthy people. You have to see people with diseases and then be like, oh, okay, this is what's like this chemical is missing from their body, and therefore the body doesn't work like that. Therefore, this chemical plays this role, right? Same thing with computers.
Yeah. So I showed the links. I can show them again. I have not read this paper. I'm not super prepped. But are we gonna dive into the code on your machine, or what's next?
Yeah, why don't I sort of give a high level overview of the algorithm or the idea, and then yes, we have no idea what we're doing, and then we can dive into the code. So the high level idea is it's going to train 2 networks. One network is called the evaluation network, I think it's called, and the other network is called the policy network.
Something like that.
And the evaluation networks, what its job is, it's supposed to look at a board and like tell you an estimate of how well X's are doing or how well O's are doing in that board.
Mm-hmm. Yep. I remember reading the AlphaGo paper and talking about this.
It's exactly from that. Yeah. And so then the policy network is supposed to look at the board and say, I think there's like an 80% chance you should move here, and a 10% chance you should move here, and etc. And then what you do is you do what they call a Monte Carlo tree search. So using the policy network, you sort of stochastically follow its suggestions to explore the game tree a little bit. And then you use the evaluation network at the leaf to say, here's how well we got in our game search. And then you sort of propagate that up your game tree. And then you use that to select your next move. And then you keep a history of the moves you actually made and how they worked out. And then you use that to train your network.
Yep. So it's just like combining three things that we've talked about on the show before. The first is the value network, which I think we've talked about, is the idea that you stare at a state and you have some like guess from the system of the white position is better or the black position is better. And you see this when you like watch chess online. And
yep, that's what like the evaluation bar is on the chessboard.
Yeah. And we've talked about Monte Carlo before. I don't know that we've done that on the show. And that's just basically you just described it, but I'm trying to play it back to you because I can see it in my head. It's where you play out a bunch of hands, basically, like play out a bunch of poker hands in front of you.
The example I helped me understand Monte Carlo the most is if you want to compute the area of a circle. So one way to do that is if you just take the unit square, you pick a random point in the unit square, and you ask the question, what is the distance there to the origin or to the center of the circle? And that says, oh, I'm in the square or not. And you do that 1,000 times. And then the area of the circle is just the ratio of how many happen to land in the circle versus how many total you threw. And so it's not exactly right, like it's stochastically right, probabilistically.
Yeah.
But it's the method of basically just picking random points, testing them, and then using statistics to compute the answer.
It's a sampling method.
Yeah, sampling method, exactly.
And then the third thing we talked about last week, I watched part of your show, or maybe we talked about it 2 weeks ago. And that's where, or maybe I'm mixing with some YouTubes that I watched on ML, where it's basically deciding that the action, right? Because these are all function approximators, right? ML, the only thing you do with ML is you make a function approximator, like a black box that knows how to, given some inputs, map what a function would do. And this one gives you distributions on the action space.
Correct, exactly.
Okay. And so then based on distributions on the action space, we use Monte Carlo as a method to explore potential future actions and use that to choose.
Yes, so I can show it to you in code. So other thing is I teched up to using Microsoft Azure Machine Learning Studio, which is a fancier way of using Azure for machine learning.
Okay.
And so what's nice about this is to just start the VM, you just click this one button. And it's going to do all the work of starting the VM and connecting it eventually. So
my big company radar can just like see how this could come to be, right? Like the ML people wrote the like ML tool to talk to the ML part of the cloud, and like somehow we're forced to add an edit in Visual Studio button, but like it doesn't actually. Anyways, I don't know. I'm imagining.
You can often like read out the organizational structure that produced a piece of software.
You totally can.
By looking at, like, clearly this bar is dominant over this bar. So whatever VP owns this bar is this whatever VP owns these things reports to that VP.
So by the way, we know we have no insider knowledge of Microsoft at all. We're just
like that's honestly why we're using Azure as opposed to something I would know more about.
Yes.
Specifically to not know anything.
Anyway, so but this sub VP plays with Visual Studio. We're not going to do that tonight. We're gonna
somewhere in here there was like a take this thing to Visual Studio.
It's right there. It's in the middle. Edit in Visual Studio. Preview or something. Preview beta. Anyways,
we're doing it on the web. Anyway, so I can show you the code that I have in here. So a bunch of imports. That's not that exciting. So this is a model of tic-tac-toe. So 3x3 grid, 9 total possible actions in tic-tac-toe. Okay. There's a player -1 who we successfully booted our VM. Thank you. player -1 is going to be O, player 1 is going to be X. And then, so last time what we did is we had our model of the board actually had 18 slots in it, where there was like a front board and a back board that we would flip. So I've switched this now, so there's only 9 slots, and then you can either put -1 or 1 or 0, meaning no one has played there. That's what this tutorial did, and it makes a lot of sense because then you can transpose the player just by multiplying by -1. So it's a slightly different board setup than we had before. Other than that, these functions are pretty much the same as what we had before.
Mm-hmm. This looks very similar. You gave me sort of a private tour on Saturday or something, and this looks very similar to what you had then. Is that, did you copy a bunch of that code?
I just rewrote it. Yeah. I copied it, rewrote it, like basically got it into shape. Yeah. So this is an important function. So this says, if I have a bunch of pieces, so pieces is like the 9x9 tensor of the pieces,
okay,
and a player, it canonicalizes this board to be as if the player was player 1 as opposed to -1. So it just multiplies the pieces by the player number.
Because the player is also a tensor that's like a rotation on the board or something like that?
No, the player is just the number 1 or -1.
Oh. So it flips all of the,
So this lets you basically apply all of the learning you did with O to situations with X.
Yeah, makes sense.
And so then there's actually an even further form of this, which is generating all the rotations of the board.
Yeah.
So I haven't done that yet. That may be a thing we want to do. But
because if you don't do that, it will end up learning. You're forcing the function to learn in quadruplicate, whatever, in 4x.
You basically just need to spend like whatever it is, 6 times the resources to do the same training, because everything you learned about the upper left corner, it's also true about the upper right corner. Yeah. And so you could just generate that data. It's called a process called regularization, where you take a training set, you transform it in all of the ways that don't make a difference, and then you train the network in all of those so that it knows that none of those transformations make a difference. Okay. But I haven't done that. So then here is the Monte Carlo tree search, which is not a thing we had last week. So it's got a bunch of different state variables.
Did you write this, or?
This I got basically from that tutorial that we linked to. I adapted it to this scenario, but like if you go look in that tutorial, you'll see exactly these same variables with these same comments. Like these refer to their code, not this code.
And so the Q values, that's the like expected outcome.
Right. That's the like estimate for how good is this in this state. If I take this action, like how good an outcome do I think that is? Yeah. So this is a hard thing to compute that we're going to basically infer from a bunch of other stuff.
Well, but that's the thing that we're approximating. That's what our function, that's what we're learning is right?
Correct. We're learning this function.
I remember there's a choice here whether we learn that function or we learn some like meta version of that, but I don't remember the words well enough to.
Yeah, we learn a slightly. We'll see exactly what the model is, but we don't learn exactly this function. So in the previous one, in the reinforcement learning, you literally learn this function.
Yep.
In this one, we learn a slightly different function, very very closely tied to this function.
And so n of state of A. I don't know, what does n tell us?
So when the way the Monte Carlo tree search works is it explores promising branches in the tree, and then it remembers how they worked out.
Okay.
And so you need to know how many times you've traversed an edge to basically know what the divisor is going to be.
I see. So the number of times that we were at state A or at state S and chose action A
was this. And this is just the total number of times we were at state S. And so if you want to know like what % of the time did I choose state A when I was in state S, you can divide these numbers.
And initial policy is first action?
So the tree search that we're going to do is all going to be with a fixed set of parameters in the neural network. And so it's going to cache the evaluation of the neural network in this data structure. And so later on, after we played a few games, we'll train the neural network and we'll throw away our tree search and we'll start with a new tree search. So this is just a cache of what the neural network returns in this state. So the neural network in a given state will give us the policy network will give us the policy P. So the policy is just a probability distribution over edges.
A policy is over potential A's, right?
Yeah, over actions you can take. So it'll say the network thinks you should put an X in the middle 80% of the time.
Okay, so just to restate, a policy is a tensor or a vector or a matrix. Any of these are all the same.
It just has 9. For tic-tac-toe, it has 9 entries corresponding to the 9 squares, and says what is the probability that we think that move is good, that's the move you should take.
And is it 0 to 1, or does it have negative?
It doesn't matter. You normalize it. So you mask out the invalid moves, and then you normalize, and then you figure out, and then you throw in an exponential in there for good measure.
Okay, and ES is the count that we ended at this state, or it is this is a terminal state?
Yeah, so this is something I changed from the actual the tutorial. So ES represents this is a terminal state in the game. The game is over. We now know the conclusion of the game.
Okay.
And so in the tutorial, they use 0 to mean the game is over. And I switched that to so they use 0 to mean the game is not over. I switched that to be none. So this thing will be none when the game is not over. And when the game is over, it'll be the score of the game. So the reason I did that is because in tic-tac-toe, 0 is a really important score because it's a draw, and tic-tac-toe is a draw. So I wanted to actually, in the tutorial, they cheat a little bit, and they use a very small number to represent a draw. So here I'm actually using 0 to represent the draw.
Are we doing sentinel values here?
A little bit. So it wants to distinguish the case of I haven't explored this state before from the case of I've explored this state, I've done the computation to figure out that the game continues. And so I don't want to repeat that computation. I just want to cache the knowledge that I've explored the state and the game continues.
Okay.
So
and valid actions is a 1 by 9 tensor showing 1 or 0 for whether the action is valid?
Absolutely.
Oh, good.
Nailed it. Again, it just caching this information doesn't have to recompute it because we're going to need it to multiply against the suggestions from the network.
Can you capitalize the A in actions? It's bothering my soul.
Yeah. Where?
No, down. There you go. Valid actions. No, up. Game, get valid.
Oh, okay. Well, it's actually called something else. We can just change it to be what it's actually called.
Oh, okay. I couldn't take it.
Sorry. They use these like non-Pythonic names, like with I also
they didn't run through PEP 8?
No, like clearly not.
Oh, jeez. Such a
what is this thing called?
Of course, Python, like the JavaScript ecosystem, has like 8 different validators.
Or in my Python down, we come from underscore down.
Eric's been a little bit busy.
we trade off. Like if you go watch some of the other shows, like Eric wrote an entire Ren VM and just like demoed it to me for many weeks in a row.
We worked together for a few years, over a decade at this point, I think. All right.
Okay, so this is the main entry point to the Monte Carlo tree search. So you say, here are the pieces, and then temperature is an interesting thing. I haven't done all the implementation for temperature, but basically, the colder the temperature is, the more likely this will select the most suggested action. If the temperature is really hot, it's just going to pick a random action.
Oh.
Which I thought it's like an interesting way of taking your probability distribution and basically saying how much you want to go by, like how much stock do you want to put in the accuracy of it. Which is, I've seen this in other machine learning things, like the language models also appear to have a temperature. So when you want to, like, when you're using a language model, you start off what you want to have writing, and then the language model will complete the rest of the essay or whatever. And you can set the temperature, which is like, how crazy an essay do you want? Like, how random do you want your essay to be?
Is temperature something you've seen in other systems, or is that an ML term? Like the term makes sense, but I think of like stochasticity or like learning rate or like.
I mean, here's the equation if you just want to see it. Like it's just divisor and the exponent. I've seen it in like annealing. So annealing, you also initialize things to a random state, and then you turn down the temperature, and you sort of cool down to some local optimum.
All right, so I just want to read this so I have some idea. Okay, so for range and simulation count, okay.
Go search.
Search. I don't know, but I'll keep going. Get repr of pieces. Okay, that's you just take your pieces tensor and turn it into some state.
So you just turn it into a string so you can use it as a key in a map. Yes, exactly.
I didn't get it, but that's okay. I was showing our before Flutter video to my wife last night, and she was just like, all of a sudden, what went on when a comment came on screen? I wonder if others feel that way. It's like they're just not used to comments appearing in the middle of our YouTubes.
I've seen other people who have like the comments come in automatically. We got to figure out that technology. We have to click on a thing. So people who comment, they're like, "Oh, there's like a delay." It's like, yeah, the delay is I have to notice your comment and click on it.
Well, that's like a Twitch technology, because when you're like, in the heat of battle, you can't go over quick. You just have to appear.
Okay. So anyway, so what does this actually do? So
that's the number of times we hit that state with that action. So that's the visit count.
Yep.
If state action in okay, so if it's in there,
give the count. Otherwise, 0. Python is has the
oh, that's right.
ternary operator is in the craziest order in Python, but this is Python. Welcome to Python. So yeah, it's the number of times we visited that state.
Yeah.
Otherwise 0 for all the actions, and then you apply the temperature, and then you just take the sum. So
in Dart, that whole middle section is question mark. Anyway,
whatever. Python is the language of machine learning. We're here visiting machine learning.
We will speak as the natives speak.
Yeah. So this is just basically reading out how we did.
Okay.
So the search takes place in the search function, which we do just some number of times every time we want to get the actions, where that number is 25. Could be anything.
Okay.
So the search function, get the repr again, probably not efficient. Then I wrap my board class around this, so I have all my functions. The pieces are just like the raw tensor. The board is like the object that knows how to do stuff. So if we've never seen this state before, then we go read out the score. So if the score is not none, meaning that the game is over, there's no more game to play.
What's E of S? That's the estimated value.
It's like the evaluation, the correct evaluation. So like it'll be 1 if O wins, and -1 if X wins, 0 if it's a draw, or none if the game is still going on.
Okay.
And then you negate it because you're it's the other person's turn that you're returning it for.
Okay.
Okay. So if the game continues, then if we haven't queried the model yet, we query the model.
Because PS is
just a cache of the output of the model.
Because the P is the policy.
The policy.
Policy at state S.
Policy at state S.
Okay.
So we query the model. So that gives us the policy at state S, and also gives us a guess for the evaluation at this board state.
Okay.
So then we say, okay, board, what are the valid actions?
I thought we were working on the policy model. Why did we get a V here?
So it turns out we use the same model will give us both the policy and the evaluation. When we get to the model, you'll see they share they share all the hidden nodes of the neural network. They're just they have different decoders in the last layer. There's a decoder that gives you the policy, a decoder gives you this. The idea being most of the representation of the game is common between those two things. You just need different decoders for them.
Okay.
So we get our valid action mask. So we mask out all of the invalid actions. And then we sum it up, and then we basically normalize by the sum. And then this is a case that means the model is broken. The model is dumb and hasn't learned very much yet. So it's giving you a sum of like 0. And
what
so
is P of S of? Oh, I see. That's the sum. of
the sum of all of PS over S.
of
So, like,
policies at S, or is it predictions at S, or I think
it's just this value here. So at this state, you look at all of the values that you got back, and you just add them up, because you want like a fraction, right? Like you want like a percentage, and so you need to know what is 100%. Well, you got to know what to divide by.
because you're trying to feed this back to the caller, like you're looking into the future.
So the model just gives you numbers, right?
Mm-hmm.
And so it's going to give you bigger numbers when it likes things more.
Mm-hmm.
But we're actually going to use this as a probability distribution. So we want that actually be a probability to be a distribution. Right?
I see. So, okay. I think if I were writing this, and not trying to pick on you, I think I would use A, some slightly different variable names, and B, some subfunctions that would like do like this whole, I can't select, but this whole dance above on 29 to 33, that feels like a function that knows how to like do this fancy negating if necessary. And then this later stuff where you want to like run the prediction and maybe then hand that thing off to a like, oh, okay, give me the normalization.
Mm-hmm.
But that's fine.
Yeah, mostly I was following the structure of the tutorial. Like I totally agree with you on the code structure. Like that's a way more structured way of doing this.
I'm just trying to feed it through my brain so that it makes sense.
Yeah, I think that people who write these things, they're very comfortable with like big math equations inside papers, and so this looks more like a big math equation inside of a paper. Whereas I think you and I both have the instinct of, okay, let's give these more semantic names and hide.
I'm just constantly trying to read the thing like it's written in English, and so I'm looking at the variable names, I'm looking at the function names, and I just assume that the function does what it says it does. And but anyways, okay, so we've normalized it down to, so it's a probability distribution.
Yep. We catch the valids and say we've never visited this node before.
Okay.
And then
some idea what we just talked through. So okay, keep going.
And then we return the estimate that the model gave us.
Oh,
that's our best
sub if in our yeah.
Yep, that's our best guess so far. Okay, so now we've been here before. Now we're visiting again. So we read out the valids that we cached last time.
Yeah.
And now we're going to explore deeper into the tree to learn more about the game. And so we're going to try to figure out what action do we actually want to take in the game right now. And this is the crazy equation it uses. And we can try to understand this. So first of all, it checks every action and only looks at actions that are valid.
Okay.
And then if we have some more educated guess about how good it's going to be to take this action in this state, then we use that information. Otherwise, we use a different equation.
What's CPUC?
So we're trying. CPUC is a constant.
But what is
so what the constant's value is 1. So what this constant controls is, so the two parts of this equation. Let's see if I can bring more of it.
This is like the learning rate or whatever.
It is not the learning rate. So this, if we only had this part of the equation, then we would always be visiting states that in our current knowledge seem attractive. And then this part of the equation says, let's take what the model said and go explore in a balanced way.
The square root of the number of times we visited that state divided by 1 plus the number.
Yeah, so this is like, if this term, just look at this term by itself, this term would tell us to go visit every possible state equally. It's like, we've been to this one 10 times and this one 7 times. We should probably go to the one we've been to 7 times because we haven't explored it very much. And so then that's weighted by how good the model thinks it might be to go to that state. So we'll say, we'll go to the one, if the model thinks it's promising, we'll go there more often. But if the model thinks it's not promising, we'll still go there sometimes in case the model is wrong.
Okay.
And so then CPUC is a constant that balances this exploration term with this exploitation term. So exploitation means that we found something good.
Yep.
Let's go do that more.
And what is this
And then-
equal to on the far left? U. What the heck's U?
U is just we're doing a search for the best U. It's called the upper confidence. That's what it's called in the paper.
Okay.
So we found a U that's better than the one we found so far. Remember that. So this is basically just finding the A with the best U.
Whoever wrote this has not worked in a 1,000,000-line code base. Just putting that out there.
This is, by the way, I haven't done one level of cleanup on these variable names. If you go look at the tutorial, they're one level more obscure.
I'm not trying to pick on the individual. I'm just saying that like a learning experience that I went through when I worked on my first 1,000,000-line code base is that no one has any idea what the whole thing does. And
So
you spend all your time reading code, not writing code. And so you have to write it gorgeous.
Yeah, but I think that these machine learning things are not like that. Like I don't think you end up with a 1,000,000-line notebook.
No, you don't. You end up with these little tiny explorations that then you compile down to a model that then is magic. So it's funny actually because I have an aunt who was like a COBOL programmer. She's retired now, but like COBOL programmer from forever ago that like built models for like actuarial tables for insurance. And like she like kept them running for whatever. And then she retired like 3 times and they kept hiring her back because it was like, something broke. Save us. And that feels like ML to me.
This is like the alternate model, right? There's some like model of where you think a software engineer's job is to make themselves indispensable by like making the most obscure, obtuse, unintelligible thing. Whereas I view my job as the opposite. Like I succeed when I've like automated myself out of a job and everyone else understands the system better than I do. And then I can go retire on the beach.
But that's also because you come from 100-person team, 1,000,000-line code base. Well, but it's like she's the only COBOL programmer, right? And
Yes.
so like, and there's one ML person who did this.
Yeah, so I can understand by talking with a friend of mine. This is like this is the way research code is like, because 99% of research code gets written once and then never run again, and then 1% of research code becomes the foundation for an entire industry.
Yep.
And like the reason I'm interested in this topic is I think they really found something here. Like this machine learning stuff really seems like it's doing stuff, and we're still in the prehistory of it. Like we're still working up to the parts that are really like the recent developments in the past 6 months or a year. Because I tried to jump in and learn that. I was like, whoa, I don't know anything about this. So I'm trying to rewind the clock some number of years, get on, like work through it with them and learn.
And I think it's going to take, and I'm sure there's like hundreds, if not thousands, if not tens of thousands of engineers doing this, but other people who have worked on other large systems in the last decade that are not ML to sort of help connect, at least my limited, I could be totally wrong, but my limited understanding of the space to help connect this to like how other large systems work.
I think it's just not another thing we've done that recently. Like, but this used to be happening all the time. Like, my understanding is that like SQL databases came out of research in the same way, and they've just been, hey, thanks for joining us. They've just been digested by industry to the point where they're now just like industrial tools that work the way you expect an industrial tool to work.
Yep.
And so there's got to be some amount of digestion of this, like these brilliant ideas here to like make it accessible to large scale engineering projects.
Honestly, as soon as you try learning ML concept, you give up immediately because it goes under. Yeah, again, I'm not trying to attack the like individual ML engineers or ML in the genre. I come from a different, like you talk about Code Town, right? Like I come from 100-person engineering team town.
And just to give you a flavor of that experience, folks, not Eric, because obviously you've been there, but folks in the audience, like if you write confusing code, what'll happen is someone else will edit the code while you're not paying attention. You'll come back to it like a few weeks later and it'll be all wrong because like it was confusing, and so the person didn't understand it. Whereas if you write code that's clear, then someone will come in and understand it, and when they need to change it, they'll make a change that's more likely to be correct. And so we talk about temperature, right? So like the like well-written, well-understood code has a nice, cool temperature. People can work with it without getting burned.
Well, I would actually even remove well from that sentence. Like it doesn't even need to be a judgment call, but just like making
the code, like, and giving the functions clear names, giving the variables clear names, just makes it less sharp. Like one of my frustrations when I used to work on C++ a lot is that C++ is a very sharp knife that you're very good at lopping your arm off, and hopefully only your arm. And like one of the things that you have to do in large systems is make them simple, make them dumb, make all the variables, really clear and the functions clear, so it's easy to do the right thing and hard to do the wrong thing. And that hasn't been done to this 100-line code base yet.
Yeah, so just to address this, it's by the way, Google has an offering just I don't know, like this or similar or better, or who knows. But part of what we're doing in the show is exploring different technologies. And so part of what I was interested in doing this project is, first of all, the content of the project. Second of all, like, what is it like to use Microsoft's cloud? I use Google's cloud all day, every day at work. I know exactly how it works. What does Microsoft do well? What does Microsoft not do well? So like one thing that I found very interesting about using Microsoft's cloud is it told me very clearly when I'm using these machines, like this machine was 11 cents an hour. The machine we're using right now is 26 cents an hour. But it turned out that my actual bill at the end of the month was dominated by the storage. Because the first time I created an instance, I think I picked a fancy SSD storage because I didn't know what I was doing, which was vastly more expensive than the compute. But it didn't really tell me that, which I thought was interesting.
Yeah.
It's important not to be parochial. If you're parochial and only use the tools you have at home, you'll never learn what the tools are like in other places.
Yeah. All right. So we had walked through this. You even fixed the variable names. I appreciate it. We've computed our upper confidence.
Well, I'll just address this one last comment, and then we'll go through and finish this function. Yeah, exactly. Like these notations, like C puck, like if you go look in the paper, it's a C with like puck as its subscript, right? So it's been like, so I've done one level of digesting where I've like named this best upper confidence. I still don't know what upper confidence is, but we'll learn. And so like, but in a macro scale, these things get digested. So this thing ends up with a name like policy score or something like more understandable. Yes.
And to riff on that one more time, it's like when you go to look at the FastAI docs, the first thing you see is the paper that it came from. When you go to look at MDN about your JavaScript function, it does not tell you what paper it came from, right? Because it's been digested 10,000 times to get there. And that's how you get to be used by 10 million engineers.
Or like a super concrete example, like if you go look at what is an outer join in Postgres, that is draw you a diagram and be like, here's what an outer join looks like. Blah, blah, blah. But where did outer join come from? It's some like algebraic construction in like relational algebra, right? Which is how it got invented. But no one uses Postgres. I mean, somebody does, but the run-of-the-mill person who uses Postgres thinks of the picture of the outer join, right?
Mm-hmm. It's very nice that person invented that. I'd love to give them a citation, but it just doesn't matter in practical sense.
Well, they've already succeeded. Their thing was the 1% of research that became the center of the universe, just like databases. Okay, so we found the best action. We were in love with this action.
Okay.
We were so in love with it, we give it the name A. So then what we do is we say, well, we want the next state. So this thing is actually a thing that knows about tic-tac-toe. We give it the pieces. We're always player one, because we've always canonicalized. And we take action A, and then the game will tell us back, here's the next set of pieces and the next player. And then we canonicalize it so that the next pieces are also expressed in terms of player one.
Why does it give us back the next player? Is the next player like a 1-by-1 tensor, or is it?
Mm-hmm. No, just a number.
But why do we always pass in 1 and always get back 0 or whatever? Oh, it's 1 and -1.
Yeah, so like other games like Othello, you can make a move and then it could be your turn again.
Oh, I see. And so this was ported from Othello, is what you're.
Which is, yeah, it's the structure comes from there, but it's just more general.
Okay, that's fine.
Okay, so then we recurse, go do a bunch more searching, and then this is going to give us back how things went.
And I've already forgotten what V is.
That's V is our
value.
V is the the value that our search turned up.
Okay.
So it's returned to us in our terms. So it's the caller negates it. So it's from our point of view.
And if state action tuple is in self QSA, didn't we ask that above?
and fill it in before, or were we going
yes.
back? Or
So now we're on the way up of the recursion. We're going to remember this information. So the easiest case is we've gotten no actual data about this state and action before, so we just remember it. We say, okay, great, that's the one value we got. We've been here once, and then all this equation does is just average in the v value. So basically, we've been to the state 12 times. We've gotten 12 different v's. We're going to remember the average of that.
Yeah.
And then this is written in a complicated way, but that's what it does.
Yeah. No, that's the whole thing with this. This code is like 20 lines of interesting code. It's just all written to be compatible with the paper and not compatible with how people read it.
Yep.
And we could beat it over the head all night, but that doesn't. But that's the core problem. This code just needs a few rounds of bathing.
Yep. So like you'd have a data structure, like a data structure that would know how to take in a value and maintain the average of all the values it had seen before.
Yeah. And some comments.
You wouldn't test the crap out of that, like have it be a name, and then you wouldn't have to like puzzle over what exactly are these subscripts and blah blah blah.
Yeah. Okay. But I can see how you write this. I'm wishing for
like for some reason ISA, like the hardware instruction or the assembly instructions, they have a like deep need to abbreviate everything.
Oh.
Like move, right, is MOV. They lost the E. Or like load effective address is LEA because they lost all the other letters.
But you like write assembly, or you can write assembly.
Yeah, we always write it in these like super cryptic acronyms.
Yeah.
Like anyway, the assembly people like to be cryptic. Okay, so that's the Monte Carlo tree search.
That was the Monte Carlo tree search?
That was it. That's the whole thing.
No, go back up.
Yep.
That what we just did was the Monte Carlo tree search.
Mm-hmm.
Oh, okay. And then great. Okay. And then the next thing we have, this is our learner, which should be very simple.
Should be simple. So it takes in the model. It's going to maintain a tree search for a while, and it's going to remember a bunch of history. So it's going to play itself, right? So this is a function that says, please go play a game with yourself and learn something about the game.
Okay.
So we start off with the board in its initial state.
Yep.
Player 1 is the one that goes first, and we're going to remember some things that we've seen.
Yep.
So basically, while true, we're going to play out the game. So we canonicalize. We ask the tree search to go find us a probability distribution over moves.
Yep.
Then we remember what we've seen. We've seen these pieces with this player and this probability choice. We pick one of the moves based on that probability distribution, and then we make the move. And then we ask if the game is over. We ask to evaluate the game. If the score is not none, meaning the game is done, we've gotten a score, then we return our observations. So our observations are the board, the probability distribution, and then the score, and then we have to negate the score depending on whether which player it is now.
So this plays one move? No, it says while true.
No, it's a loop. It's going to keep looping through, keep playing moves.
This is until someone wins. Yeah.
Until somebody wins, and then it's going to report back all of the states and the transitions that it saw, and then it's going to report back who won at the end.
Yeah, so this function is actually doing a couple sort of distinct things. And here again, I would factor out what is the plan that you're using. You happen to be using a random. So if you put an enter after the observations line, that action, that choosing the action is like a separate thing that this function is doing.
Correct.
It's implementing a policy for play.
Right. The policy for play is take an action according to the probability distribution.
Oh, I see. Yes.
So it's sort of the natural
random one.
Yeah, it's saying weight my choice of action by the probability distribution I got back from the tree search.
Okay.
So then the learning loop is pretty straightforward. We just spin for a certain number of times. We remember a bunch of observations. We decide in each iteration how many games we want to play. So these are just constants. We go instantiate the tree search. We play the game, remember what we saw, keep remembering what we saw. And then once we're done playing the game a bunch of times, now it's time to update the model. So we basically smush all of the things we saw into a single data set. We shuffle the data set, and then we train the model based on that data set.
We smush all the, okay, so we learn for range and iteration count, yeah. We, observations.
I think there's a bug in this function, by the way, but go on. Yeah.
TQDM. What is TQDM?
Oh, this is cute. This is Python for print me a progress bar during this iteration.
Okay.
It's super cute. I kept it.
In TQDM, okay. Do our Monte Carlo tree search, we change it every time. Why would we put it in self? I don't know. I see, because we use it by the play game. So we initialize our Monte Carlo.
Right, so let's refactor this code to not be terrible. So
not just store it in self randomly for no good reason.
Right. So like,
and instead just pass it into the play game.
Correct. So let's just put it here.
Since where there's no tests, I worry that we're just breaking it suddenly, but that's fine. Miley, you want MCTS, yeah.
First of all, I have some tests at the bottom.
Oh, go you. Oh, you made it upper confidence.
Oh my God. Monte Carlo tree search. Yeah, I learned how to make tests in notebooks.
What? You're living in the future.
I'm living in distinctly the present. Okay, so now we make an MCS, we pass it to here. Great.
Yeah.
So just state the obvious, just to be clear. Now it's much clearer what the lifetime of this thing is.
Yeah. This was supposed to be an ML episode. It's really a critique organizational structures and code.
I just can't not. Like, I know.
Like, okay, so remind me what a deck is? Is that a
doubling the queue? It's just, think of it as like a vector with a capacity. So like if you put more than 20,000 things into this thing, instead of growing forever, it's going to just forget the old one.
Oh. What? But I see.
So I think this is wrong. I think this is extend.
What was it? Add?
It was plus equals. I want to take all of the game is going to give me a bunch of observations, and I want to just add them to this. I only want to keep track of 20,000.
Isn't that what plus equals does in Python? Is it extend?
No, I think plus equals. Oh yeah.
Okay,
you're
the same as extend in Python.
Okay.
You're thinking of add versus extend, right?
I think of append.
Append, yeah. So append would take a list and make it a sublist in your list, whereas extend will splat out the list and concatenate it.
I want to splat it out. So this thing,
which I believe is what plus equals does.
Yeah, so this thing remembers all my observations, and then after I played 100 games or whatever it is, then I'll take all the observations I accumulated and add them to my history.
Okay. And then your data set is equal, you empty it for observations in history. We take...
I flatten history, shove them in the data set, and then train
what's the self here? Like...
So I cut out a bunch of code, but like history appears to be very, very valuable information. So in the tutorial, there's all this code for saving history to disk so you don't lose it. Like your...
It's your probability distribution over board states. Like, why would you ever want to chuck that?
Yeah, so like this thing is going to grind for a long time. Like this is where all the grinding is. And then the output of it is this history. And so the history is very valuable. So we want to keep it.
I think it's a lot more valuable in Go and Othello and stuff where your distribution, so you only have 9, you have 9 board slots. And
yeah. It's going to memorize the entire game. Like if it's a halfway decent neural network, it should memorize Tic Tac.
Yeah, it'll save every single possible board state in its little tiny tensor. Okay, so
but roughly what this is doing is it's playing the game a bunch, remembering what happened, and then every once in a while retraining the model based on the data.
So I'm sorry, data set for every observation in history. We then retrain the model.
Yep.
Okay, I kind of get this. Again, I would break this into subfunctions, but yes.
Okay. So here's our neural network. Here's the whole thing.
Okay. So 9 in, 32 out, yeah. And then remind me what a ReLU is?
ReLU is a rectilinear function. So basically, it's goes from negative infinity to 0. It just flat lines at 0.
Yeah.
And then once it hits 0, it starts just being x equals y.
And
so
this is the magic that makes the universal approximation theorem work, right?
It's nothing magic about ReLU. Like any nonlinear function here.
But you need a nonlinear function. That's what the universal approximation theorem says.
Correct. If you didn't have any nonlinear functions, then the linear matrices, you could just multiply them all together and have one linear matrix because linearity composes, right?
Yeah.
So I don't know. We do this a couple times.
But to restate for the viewer, that's my understanding of the whole magic of machine learning is that they are function approximators. These neural networks that we train are function approximators. And there is a theory called the universal approximation theorem that says if you have weights on a nonlinear function, you can approximate any function with a sufficient number of weights.
I think the theorem actually gives a function of a particular form. It says you can make your matrices big enough in this form so that you could then approximate.
Okay.
Just join the stream. Hi, Rich. Thanks for joining us.
Also, for
Vertex Workbench Notebook. Okay. Should we check out Vertex Workbench? I'm totally into trying all these different notebooks. They all seem really neat. So anyway, so then the next thing is there's so this is the encoder. And then the decoder is, we have two different decoders. We have one that'll decode to a number of actions and one that decodes to a single value. And so this is
where the forward is how we're linking them together?
Yeah. So the forward is what's actually called when you want to evaluate the model. So basically we reshape the input to be the right geometry. We pass it through the first linear, the first ReLU, the second linear, the second ReLU, and then we get these values. And then we pass them through this third one, which gives us the action counts, and this fourth one that gives us just the one value, and then we output some transformation of those values.
And is this PyTorch or what is the?
This is PyTorch.
So FastAI, it had a declarative syntax for making your models. You make your models. This is using an imperative syntax. Every time you call it, you imperatively take your out value and shove it through the model. Like the model is encoded in lines 12, or the connections within the model are encoded in lines 12 through 18.
Correct. So FastAI has a bunch of machinery for applying machine learning to various different domains, like images or text or whatever.
Yeah.
I didn't see a FastAI machinery for applying it to games, but like conceptually, FastAI would have all of the code that we've just typed. It would be like.
But what I'm saying, and maybe it was TensorFlow that did this, because I think we played with TensorFlow briefly too, was I would expect to have to either declaratively explain your model connections or to have had this compiled. Whereas here, every time you execute the model, the connections of the model, like which layer feeds into what next layer and how, is encoded in this forward function, rather having been compiled once.
Yeah, that's true. But there's also a function that's like, go run this function once and remember it for me. Like it's not expecting you to do anything super fancy in here. Oh, that's the Google managed one. Oh, okay, cool. I looked into Jupyter notebooks from last episode and found a notebook kernel across. Oh, cool. We were talking about this in the last episode that like conceptually it would make sense to have notebooks for different languages like Dart or Rust or whatever. It's really neat that there is one for Rust. I'll have to check it out.
Okay, so this is our model. Cool.
Yes, and so this is the main function I haven't done yet, but it was just a wrapper to get a prediction of it. So you say some layers have states that care about whether you're evaluating or training. So this is like some weird PyTorch thing. You have to say, okay, model, go into evaluation mode. And then it doesn't leave, which is a little bit squirrely.
And what does that mean to have state that care? Is it like lock down the node values or something?
Not exactly. So there's, for example, there's a kind of layer called a drop layer. So what the drop layer does is during training, it'll randomly delete edges from your network. And the idea is it's supposed to help your network not overfit or like memorize inputs, because those inputs might be deleted out. But then when you actually do evaluation, it doesn't actually delete anything. It actually has all the edges there. And so some layers in your network could behave differently during training and during evaluation.
This all feels like we're playing at like a super low level.
Ah, cool. Yeah, there are a bunch of like people inside Google who are excited about Rust. I bet there are people inside of every software engineering shop that are excited about Rust.
It feels like we're playing a super low level, and like things like in the fast AI, the like where it's like, oh, insert an image here. This is the like image model or whatever. Like that feels like the appropriate level to be engaging with machine learning at.
Yeah, we're definitely like one level below the fast AI level. Like we're like if we were doing in the equivalent thing for images, fast AI would have done all of this stuff for us. And so we're sort of like whenever you're calling functions like no grad and stuff, like you're I don't know, I feel like you're working with this like stone tools. But
well, it's just
the point. Yeah,
I was talking with a mentee today about sort and like the various different sort algorithms. It's like reality, like I've never had to implement quicksort in my entire career.
But it's important to know how it's done.
To have some idea that there are different kinds of sorts and stuff like that. But like we're down at the like let's write our own sort, which is fine.
Well,
but,
like if you go back in the history of this channel, you'll find a very early episode where we started parsing a WAV file, right? Yeah. We were like, we're parsing a WAV file level of WAV file, for people don't know, is a sound file from the ancient past where like sound form is just like literally written down. It's like a bitmap for sound.
Okay, so this is your model, which is only partially implemented. We haven't implemented train.
I think it wraps your code and it makes it a shared library and DL opens it. That's terrifying. Like, wow. I mean, dynamic's gonna dynamic, I guess. There's dynamism somewhere where you can make executable pages with DL open. Let's do it.
It must be a very different experience than Python, though, because you can't like have an incomplete Rust program in one.
Yeah. Like, Rust really wants your code to be right.
How's the borrow checker going to get, understand that?
Anyway, that's it. That's all the code in here. This is just a little cell where I was playing around with it. And then here are my unit tests. So if I run this whole thing.
Yeah, I'm sorry that I used all of our time just, trying to have you walk through your model. But how does it work today? How far are you?
How far am I? Well, let's see. Go here. So if you don't use the learner, if you just use the model to predict things, the model can make random predictions.
That's good.
So we could try. Maybe we'll have the.
I think you implemented learning as part of your Monte Carlo, your learner. Yeah,
right? So let's have the learner try to play a game. Maybe that's a good thing to do first. So
it's okay. We're going to solve machine learning in the last minute and 20 seconds.
We're not like I don't have anything. Okay, so I got to make my thing. Research my model. Say learner. The game. Now that we've refactored it, I have to actually do this. Game. Okay. I'm kind of expecting this to blow up because I've never actually tried this before.
Float object cannot be interpreted as integer.
I agree. Floats are totally not integers.
I am surprised that Python checks at that level.
Oh, I messed this up somehow. So this is NumPy random choice.
Maybe it's the other way around.
Like
the pi and the linpy.
The computer is super laggy from streaming.
Morse code says suggestion AI for lambda bound. So
yes, yeah, you read our minds, by the way.
This is where we're trying to tech up to like tic tac toe, so you could imagine. I would love to get to the idea where we could do something slightly more sophisticated, but we got to learn to crawl before we can walk or run, for that matter.
Yeah, I think I totally just put these arguments in the wrong order.
Yeah, that common. I make that kind of mistake all the time.
I come from Type Town. Like I wish it told me this.
Oh, I know.
Oh, I need to go. See, it's not quite like hot reload. It's not just enough to go edit it. I have to reevaluate it. And then it leaves a bunch of garbage in my state.
You've lived in hot reload too long.
Okay, what's it bad about now?
Runtime error. Boolean value of tensor with more than one value is ambiguous. Boolean value of tensor. Oh, I see.
Oh.
It's saying the tensor has more than, it's not a 1x1 tensor. And you're trying to if it. Where?
What is valid action?
Is
these are tensors.
Why a tensor?
I just need to get item because it's giving me a 1x1 tensor. And what I want is the thing inside there, maybe?
Is it item or value?
Item is the thing that will extract the value from a 1x1 tensor.
Okay. Only one item element tensors can be converted to Python scalars. So I think the code would work. The problem is the pieces x, y, x. Can we just print that? I think has in it a non 1x1 tensor.
Yeah, so I think something must be like vectorized here that I'm not expecting. Like I bet if I print out the pieces.shape, it's going to have the whole batch in it or something.
Yeah.
I mean, we're not going to actually get this to work.
Yeah, no doubt. Well, I appreciate the tour. I feel like I can maybe actually hack on this with you, although we do need to find a setup that is not your private Microsoft Azure Learning Studio.
Yeah, this environment, we need to like tech up to VS Code and get our live share thing going.
And like GitHub.
Yeah, but just to be transparent, like this is what I would do to continue, right? I would start getting play game to work, go fight through all these type errors, figure it all out, then get the episodic thing to work, and eventually I'm gonna have to implement this train function, which it doesn't do anything complicated. It just basically takes the data set, feeds into the model, and then applies the optimizer or whatever. Like it's a fairly standard kind of recipe.
Yeah, and before we go, so just to restate, this is the tutorial that we were working from. This is the code that we were working from that inspired this. We didn't actually work from there to tic-tac-toe. We worked from there Othello to solve tic-tac-toe, but they also have a tic-tac-toe, which we can check our work at some point.
If you want to just clone their repo, like they have it all fully like working and like lots of cool stuff.
Yeah. And to answer Morris, one problem with Lambda Battle is the presence of random news. There might not be an anomaly. I don't think Lambda Battle is going to be the thing that we apply an agent to, but that could be fun. Yeah. I'm excited to apply agents to very simple games when we get there.
Yeah, it's kind of the fun. Like we've done a bunch of games and we've written by hand agents, so thought we could like do some machine learning agents.
So, well, this was great. Thank you for the tour. It's great to be back, and I suspect we'll do some more ML next week, but maybe like actually typing some code. So
yeah, we'll get to actually like maybe making some actual moves in tic-tac-toe.
So thanks all for stopping by, and we'll see you all next week.
Yeah, see you next week. Thanks for coming.